Okay, this is the key to exercise set 1.6. First one, using the table below, this is kind of cumulative. We got some older problems here that you need to know for your test. So make sure you've got your toolkits open. They're also available online. The keys are available online, so you can refer to those. But I would recommend have them open while you're solving these. So we want to find the area from 0 to 4 using four trapezoids of equal height. So I think always helpful when you come across one of these problems is to try and visualize this. So I would sketch it out, draw an axis, and let's plot some points 0, 3 right here, 5, 1. So I'm going to kind of sketch where these places are. So we got 0, 1, 2, 3, and 4 here. And this will be 3. 1 is at 5. 2 is at 8 up here. 3 is at 6. It's roughly here. And then 4 is at 2, kind of down here. Okay. So you see how I did this? So this is essentially like X and Y. You can think of this as Y, right? So I have 0, 3, 1, 5, 2, 8, 3, 6, and 4, 2. And I'm gonna make my trapezoid. So I'm gonna have a trapezoid connecting these two, a trapezoid connecting these two, a trapezoid connecting these two, and a trapezoid connecting these two. So that's 1, 2, 3, 4. Four trapezoids, which is what I want. Okay. So for the sake of this, let's call this, make it easy, let's call this after trapezoid A, trapezoid B, trapezoid C, trapezoid D. Now to solve this, you need the equation for a trapezoid, which is 1/2 times the width or the height, right? Let me change it to height. I say width because it looks like width based on how we're doing it. 1/2 times the height times base 1 plus base 2. That's the equation for trapezoid. So with all the information that we have, we can solve these. We can do this. You're just plugging in. Okay. I would love for you to, if you haven't done this, try right now. I'll do the first one I'll do the first one with you, and then I want you to try the other ones. Okay. So for A, for example, trapezoid A, it's going to be 1/2 times. Now, what's the height of all of my trapezoids? Remember the height, I know this is why I called it width because it visually looks like the width, but the height is this portion right here at the bottom, the distance between the points right here. And because we're just counting by 1, 0 to 1, 1 to 2, 2 to 3, 3 to 4, the height of all of them is just 1. So we don't even need to worry about the height for this because it's just 1. I mean, I'll write it for the first one just for this so you know I'm not forgetting about it, but it's just 1. So that's not going to change um, our equation, right? And then we have B1 plus B2. Now that part is a little trickier. Now B1 and B2, we're getting from visually it's the height. When we look at it like this, it's the height. So this is B1 right here, and B2 is right here. So B1, my height at 1 is 3. So you put a 3 here. Plus my next height is 5. So the area of the first trapezoid is 1/2 times 1 plus 3 plus 5. For trapezoid B, we do 1/2 times 1 times what? What are my bases for B? Well, we're double counting this one because this is B2 for A, but it's also B1 for B. If you see that, it's a shared height for both A and B. So we pick up where we left off. 5 plus 8. Trapezoid C is 1/2 times 1. Again, you pick up where you left off. 8 plus 6. And then trapezoid D is 1/2 times 1. 6 plus 2. That's it. Okay. Again, like visually, this is the 2, this is the 6, this is the 8, this is the 5, this is the 3. So like, those are my bases. I'm getting them from the heights of of my trapezoids. Visually, it's a height, but what we call base 1 and base 2. And then you're just going to add all these up. So you're basically going to do A plus B plus C plus D. Okay. And this is in toolkit 1.3 as well. So let's do it. I'm gonna write it out in a different way. So we're adding all these together, right? But really, since they all have 1/2, what I can do is just put that 1/2 out front, and then add up 3 plus. See how I have 2 5s here, so I can do 3 plus 2 times 5 plus 2 times 8 plus 2 times 6 plus the 2. So let's add this all together in my calculator. That's 3 plus 10 plus 16 plus 12 plus 2, all times 0.5. I get 21.5 units squared. So, I mean, you don't have to write it out in this form. You can just evaluate each of these individually and add them up. You can write them all in this form. I wanted to bring this up because I went over this in the toolkit in this form, and I wanted you to see how that came from. So again, this is your first this is like B1, and then this is your last base over here. So you can think about BL, I suppose, like the last base, and then in the middle, your inner bases are all counted twice because they count for 2 trapezoids in between. So you don't have to write out like this. You can just find the area of each trapezoid individually and then add them up, or you can write it in this notation. It doesn't matter to me. Okay. But you should get 21.5 units squared in the end. Next one, expand and evaluate the following sum. Again, this is from toolkit 1.3. So this is where we start at -2. This is where we finish at 1. So I want to evaluate all the values from -2 to 1 and add them together. So again, visually what this looks like is I'm doing f of -2 plus f of -1 plus f of 0 plus f of 1. That's what I'm doing. I'm plugging in -2, -1, 0, and 1 into this, and I'm adding them all up. So what that looks like is let's plug in -2. I'm going to get 2 times -2, right? Times 1 minus -2 squared. All I did was take -2 and plug it in for k. That's all that is. All right, so this is this one here. That's k equals -2. And then I'm going to add -1. 2 times -1 times 1 minus -1 squared. This is k equals -1. I got 2 more to do. K equals 0 and k equals 1. Plus 2 times 0 times 1 minus 0 squared. This is k equals 0. And then plus, I know it's getting a little messy, 2 times 1 minus 1 squared. This is k equals 1. So again, your summation means that you're adding. You're going to be adding different values. And the values that you're adding are when you plug in this number into the equation, then the next value into this equation, then the next value into this equation up until we get to 1. We finish at 1. So I'm plugging in all the values from -2 to 1, like all the consecutive numbers. So -2, -1, 0, 1. I hope that's clear. Now we evaluate. So this first one, again, I'm just doing in the calculator. This is just arithmetic. 1 minus -2, this is 3 squared. 3 squared times -2 times 2, that's -36. You can do this in your calculator. That's -36. That's 9 times -2, -18 times 2 is -36. This one, 1 minus negative 2, that's 2. 2 squared is 4. 4 times negative 1, negative 4. Negative 4 times 2, this is negative 8. Okay, all of this is negative 8. All right. And this one, see, I have a 0 here. So I have 0 times things. This is zero product property. Doesn't matter what my other values are because this is 0. The whole thing is 0, right? 0 times 2 times 1 squared is 0. Same thing here. We have 2 times 1 minus 1. This is 0, right? Because 1 minus 1 is 0. 0 squared is 0. The whole thing multiplied would be 0. So all I have is negative 36 plus negative 8. That is negative 44. Okay. Next one. 3. Evaluate the values indicated in the table based on the graph below. This is from Toolkit 1.4. I think we're getting pretty good at these. So let me move this down a bit. Limit. So first of all, what is f of negative 1? That means you just plug in negative 1 into the equation. Notice it's kind of hard to see on my video, but notice one of them's open, one of them's closed. Which one do you take? Remember, the open one gets very, very close, but does not touch. The closed one is the one we want. So this right here, this is f of negative 1, which is 4. Okay. What's the limit as x approaches? You know what? Let's do the left and right first. This comes later. Limit as x approaches negative 1 from the left side. So we're going towards negative 1, right? This is negative 1 right here. This time we're going from the left. So as I approach from the left, the limit is 4. As I approach from the right, though, I'm approaching negative 1 from the right side here. I get to 1. So the limit overall, remember this is the overall limit right here from both sides. Because this is 1 and because this is 4, the limits are different. The limit does not exist. G&E does not exist. F of 2. When I plug in 2, what value do I get? See, it's open up here. Kind of hard to see, but that's open. This is closed. I want the closed value. That's what my function equals. So when I plug in 2, I get negative 2. Limit overall of 2. So this one is skipping the left and the right section. So you're just asking for the limit overall. When I approach 2 from the right, I get negative 2. When I approach 2 from the left, I get 4. See how they're different? See, there's a jump here. That means the limit does not exist. D&E. The limit needs to be the same from both the left and the right for it to exist. Okay. As x approaches 4, what's the limit? Let's go to 4. Now, notice how the function is defined here at 4 at 1. But that's not the limit. The limit is what we approach. So as I follow my function towards 4, what is the output approaching? The output is approaching negative 4. Okay, but the value of f of 4, when I plug in 4, I get 1. Okay, backside. Okay, backside. Number 4, determine all values from 7. This is not an xy coordinate. This is an interval. It's saying everything from negative 7 to 6, where the function shown is not continuous using the 3-part definition, continuity, state what type of discontinuity is shown. So we're going from negative 7 over here to 6, where are we discontinuous? Well, visually, guys, we should be pretty good at this. And I'm sure, go ahead, if you haven't done already, identify where it's discontinuous. We're discontinuous here at negative 7. We're discontinuous here at x equals negative 3. We're discontinuous here at x equals 2. And we're discontinuous here at x equals 4. 4 discontinuities, right? 4 places where I'd have to pick up my pen, right? What are they called? So this one right here, this is called a removable, right? Because it's like you took a point out and put it somewhere else. Discontinuity. That's removable. This one's just a straight hole. I removed something, but I didn't place it somewhere else, right? It's like you see the difference between these? I've removed a point versus this is just a hole. Okay, this is the jump, right? I'm jumping up to some other point. This is a jump. And then this one over here, this is a called an infinite discontinuity. Basically, it's a vertical asymptote. Okay, so we have the types, we have the locations. The next part is identifying the why using the three-part definition. So remind the three-part definition. That's a thing you need to memorize. You need to know the three parts. Okay, so test yourself right now. Do you know them? 1, 2, 3 parts. Number one, what is it? That's right. The limit exists. Limit exists, meaning, in other words, limit from the left equals limit from the right. That's what that's saying. So that's kind of hard to read, but that's saying limit from the left equals limit from the right. Number two, f of a is defined, meaning there is an output for that input. It's not a hole or an asymptote. And then three, that output equals the limit. That's it. I went over this in exercise set 1.5. So if you are stuck on this, check out 1.5. But I'll go through them. Okay, so we have our four points. We have x equals -7. We have x equals -3. I have x equals 2 and x equals 4. And so I'm going to tell you which rules I break. So number one, does a limit exist? Yes. So because our function ends here, I cannot take a left-sided limit here, right? You see that? But the limit is approaching this value. The limit exists at -7, right? If it's not defined on the left, like there's nothing on the left and it only approaches from the right, we're fine at 1. Okay. 2, is it defined? Yes, it is defined here. When I plug in -7, I get roughly like, it looks like 4. So that's fine. We are defined. And then 3, does it equal? No, that's where we fail, right? Where the output does not equal the limit. Okay. -3. So if you look at -3, do we have a limit that exists? Yes, because the limit from the left equals the limit from the right. So 1 is a check mark. 2, is it defined? No. So notice there's a hole and there's no filled part to it. So it fails 2. And because it fails 2, it must also fail 3. Because if there's no f of a, if f of a is defined, then how can an undefined value equal the limit? Okay. 2, we have a jump here. Does it pass number 1? Does the limit exist? Does the limit from the left equal the limit from the right? No, it does not. See that? These two do not equal. Fails number 1. Number 2, is it defined? Yes, it's defined. Do I have a solid dot at 2? Yes, it's defined. 3, do they equal each other? No, they do not, because the limit does not exist. How can something that does not exist equal the output? Okay, last one. Number 4, does the limit exist? Is it the same from both sides? Nope. From the left, we get to infinity. From the right, we get to -infinity. Fails number 1. Is the function defined at number 2? Nope. Because when I plug in a 4, it's a vertical asymptote. There is no value. Fails. And therefore, it also fails number 3. So how can something undefined equal something that does not exist? It fails all 3 of them. Okay. So again, memorize these. Memorize. You need to know them. Okay. Exists, defined, equal. Okay. All right. This is kind of a preview of where we're going in calculus. So we have Zuaib is anxiously waiting for the results of his calculus test and is pacing back and forth as shown in the graph. So it's always good to kind of connect the graph to what the explanation is. So if we're pacing back and forth, right? We're going like we're moving away and then we're coming back. Okay, so the question is, at which point A, B, C, or D is Zweib's speed the greatest? So what does speed mean, right? You kind of have to know what speed is to answer this question. So speed is the distance per time, right? It's basically when you're going the most distance over the least amount of time. So here you might guess, oh, it's A, right? Because A, I'm going the most, like I'm going the most positive. But does speed care about direction? No. So actually, C has the greatest speed because it's got the steepest slope, right? So I'm going the most distance over the least amount of time, right? Even though I'm going backwards, I can go backwards and have the greatest speed, right? Speed does not care if I'm going forwards or backwards, okay? So the correct answer is C here. It's the steepest slope. Even though it's negative, it's okay. Now, the next one is asking about velocity. So this is the difference between velocity and speed. So velocity cares about direction. This is, right, when I'm going away here, when I'm moving up, this is positive velocity. When I'm going down, this is negative velocity. So moving up is positive, moving down is negative. So if I care about positive, negative, then A is correct because that would be positive. This would be negative velocity, so that's not going to be greater than a positive velocity. Okay, what is the difference between speed and velocity? So speed is always positive. I guess is a way of saying that. Speed is always positive. Does not care about direction. Velocity can be positive or negative depending on direction. I mean, there's different answers to this. This is like you could have put different things here, but generally, like, speed is always positive, and velocity um, depends on direction. Like velocity is speed with direction. Okay. Um, Next one, we're writing a sequence in summation notation. You remember, use your toolkits if you need to. If you're stuck, so summation notation immediately. Summation notation, you're drawing your sigma. Like there's some basic things to get started with this on in terms of like what you can do. You know you're going to be using sigma notation. You know you're going to have some kind of an argument here. And remember, this is the argument. And you know you're going to have an index, like a beginning point and an end point. Now, the beginning point and the end point are easy to find based on how many terms we have. So that's when you're going to you just want to count them. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 terms right here. So I know I'm gonna start by saying x equals 1, and I'm gonna finish at 8. This guarantees me 8 terms. 1, 2, 3, 4, 5, 6, 7, 8. 8 terms. So you get points just for doing that. Okay. The tricky part is figuring out the argument. Okay. Now I'm gonna start at 9 and I'm gonna end at 23. If you notice, the change between each of these is plus 2. 9 plus 2 is 11, plus 2 is 13, plus 2 is 15, plus 2 is 17, plus 2, and so on, and so on, and so on. Which means that, in my argument, I want to be adding 2 for every x. Every time x goes up, I want to increase 2. And then what do I start at? What do I start at? Well, here, it looks like I start at 9. But here's the thing. Your first value, you're going to plug 1 into this equation, right? If I plug 1 into this equation, I'm already at 2. So I don't want to start at 9. I actually want to start at 7. Okay. You could also write this. So this is correct. This is a correct answer. You could also write it as the summation from 0 to 7 of 9 plus 2x. This is also acceptable. And you can always test it by plugging it in. So for example, for this one, I could say, the reason that this works is because you're plugging in 0 as your first value. Your first value is going to be 9. So we're going to have 9 plus 2 times 0 plus 9 plus 2 times 1 plus 9 plus 2 times 2, and so on. And if you expand this out, you will get 9, 11, 13, 15, 17, and so on. Okay. 7. Use summation notation to find an expression estimating the area of the following region using 15 right endpoint triangles. The area of f of x on the interval 4 to 9. So again, using your toolkit 1.3, this will help you a lot. So again, summation notation, you can start by drawing your sigma. That's a good place to start. And we know we have 15 right endpoint triangles. So that means I'm going to need 15 numbers here. So I'm going to go from 1 to 15. So there's two situations here. For right endpoint, you start at 1 and you go to the number you want to end at. If it was left, so I'm going to write like a different scenario. Like if that said left, what you would do is the same thing, but you would start at 0 and go to 14. This is still 15 rectangles. But the reason we start at 0, I'm going to kind of show the visual here. If you got like a function and I'm taking remember, like basically you're trying to find the kind of the heights of each of these. If I want left, I start at 0 because I want to count that first left side. So this is basically 0. And then this would be counting the right side, the first right side. That's when you start at 1. Okay, we're going to go through the rest of this. So we need to find the area from the interval 4 to 9. We have 15 rectangles. So if you think about rectangles, the area of a rectangle is base times height. So we need to find the base and height of all these rectangles. The base is the easy part, because if you think visually, we have some function and we're trying to find the area from 4 to 9. And we're going to have 15 rectangles. This is not accurate, but I have 15 rectangles in between 4 and 9. Okay. How wide are these rectangles? Well, if you have 15 rectangles and the distance between this is 5 and they're all equal, we just divide 5 by 15 and we get 1/3. So each of these rectangles right here, each one of them has a width of 1/3. Okay, so that's the easy part. So we have 1/3, and we can add that to our summation right here. We're gonna have 1/3 times, now we got to figure out the heights of all these. How do we figure out the heights of all of them? Well, you're going to find the heights of all of them by plugging in the x values into this function. Now, I don't know the function. That's okay. I don't need to know the function, right? It's fine. I just know that I'm plugging in these x values into this function. So it's going to be 1/3 times the height, which is going to be f of, now here, you're going to write down. So see that my first x value is 4. So I'm starting at 4. Okay. And then I'm going to add 1/3 for every x. And this is it, guys. This is the summation. So let's recap. We have 15 rectangles. That means right here I need 15 numbers. So from 1 to 15, that's 15 numbers. 1/3, this is the base. Like these are how wide my rectangles are. And then this f of 4 plus 1/3 x, this is the height. Okay, so 1/3 times the height 15 times. This is going to make more sense when we use an example. So let's say that the function what is x squared plus 2x. What is this going to look like? Well, this thing is the same, right? But all we're going to do is replace. Yeah, I'll show you. So it's going to be from 1 to 15 of 1/3. But instead of f of 4 plus 1/3 x, let's write in this function instead. So it's going to be, instead of x, we're going to have 4 plus 1/3 x squared plus 2 times 4 plus 1/3 x. This right here, so again, this is the base, this is the b, the base, and this is the height right here. It's the output of the function when I plug the x value in. I'm plugging in an x value. This is just a regular 4. That line is kind of a mistake. This is the 4. So again, like what you have, what does this function look like? X squared plus 2x is like roughly a parabola around. It's going to look something like this, right? Roughly. It is a parabola, but it's a little bit different because we're plus 2x. And we're going from 4, let's say 4 here to 9 here. Okay. We've got all the bases, right? These are all 1/3. And then to figure out the heights of this, we're plugging in the respective x values into the function. So you're starting at 4 1/3, plug that in, you would get f of 4 1/3 right here. Then you would plug in this, you would go to 2, because we start at 1, we would go to 2, you'd find the height at f of 4 2/3, and then you get that height. And then you multiply that by 1/3. And basically what you end up with is 15 different heights and times 15 1/3, and you're adding them all together to get the total area. If you understand that, that's okay. I'm gonna explain that one more time in case that's not clear. So you can stop the video now if you want to, but if you're still confused, I want to get another piece of paper. Okay, this will do. So, again, I want to make this super clear. So I'm going to rewrite it. This is our function, x squared plus 2x. It looks roughly like this, and I'm going from 4 to 9. So I want to find this area right here by finding the areas of a bunch of rectangles between here. It looks like this. So visually, this is what our function looks like. Again, like these are not necessarily accurate rectangles, but this is roughly what it looks like. And remember that each of these is 1/3. So that's where I'm getting that from. The 1/3 is there. And there's 15, and that's shown by x equals 1 to x equals 15. And this is the base. And then the height is shown by the output of the function at these points. So you say f of your first value. If I wanted f of 4, it would just be f of 4, right? But the thing is, because it's right-sided, I don't want f of 4. I want f of 4 1/3. So you say plus 1/3. And then x, because I'm going to keep going by 1/3 every single time. So your first, if we found f of 4 1/3, let's do this over here. This is the function. F of 4 1/3 would be 4 1/3 squared plus 2 times 4 1/3. Okay, so 4.33 squared plus 2 times 4.33. It's roughly 27.4. So I'm gonna this is gonna be a zoomed in version. of what we're like a micro version of what we're doing. So this is 4 right here. This is 4 1/3 right here. And this is 4 2/3. Okay. So when I plug this in, what I found was the height of this is 27.4. Okay. So in my summation, for my first rectangle, when I plug in 4 1/3, I'm getting 1/3 times 27.4, and that's going to give me the area of this. Okay. Then for my second term, right, then I'm going to plug in 2 into this. I'm going to get, right over here, f of 4 2/3. Okay, and that's going to be 4 2/3 squared plus 2 times 4 2/3. And so what that becomes, I'll do it on the calculator, 4.66 squared, that's 21.7 plus 2 times 4.66 is roughly, together this becomes 31 roughly. So the height of my next rectangle is 31, and that's going to be multiplied by 1/3. So I would find then now I got the area of this one. So that's what we're doing. We are multiplying 1/3, that's the width of each of these, times the height, which is the output of the function at their respective x values. This is right-sided. Now, for left, I'm going to cover this briefly, but for left-sided, it's the other way around. What I mean by that is, instead of taking this right side, you take the left side. So it looks something like this. This is a micro view of it. So with the left side, if we think about our summation, right, the function stays the same. Like the argument stays the same. It's going to be 1/3 f of 4 plus 1/3 x, right? But my first value, I want to be a 4. Not a 4 1/3. See, here I wanted it to be a 4 1/3 because I was taking the right side. Here I want it to be a 4 because it's the left side. So instead of starting at 1 here, for a left-sided one, you start at 0. So you go from 0 to 14. This still gets us 15 rectangles, but it gives us the left side instead of the right side. Okay, so this one here would be left side Riemann, and this one up here would be the right side Riemann. Okay,